the code name for our model is FMV3, that's what we call it. But you'll also see it referred to in the TC community as the Google DeepMind Ensemble or the Google AI model, or if it's coming from the NHC suite, then you might see it as GGMI in the ADEPS. All of this refers to the same model. So we launched this model operationally in June 2025. On the left-hand side, you see a snippet of some highlights from the season. We had a pretty good season. Well, we got our base weather model, which could predict everyday weather very well, and then we fine-tuned it and trained it with best track data from the IBTrax record. And that, it sounds kind of simple, yeah, it's kind of simple. That was basically all we did. And once we've done this, once the model is trained, we can run the model in real time and produce IBTrax-like predictions. So essentially, the model is trying to predict what IBTrax would have recorded. So we get latitude, longitude, Vmax, and the 34, 50, and 64 knot wind radii in all four quadrants. We then run a tracker on top of those predictions, and we get something like this. So this is obviously Milton, prediction for Milton from our model, and we can directly predict from the initial atmospheric state from ECMWF the wind speed and the radii, as you see there. I thought this community might be wondering, why does AI do so well, you know? Like, what's actually going on? So I would frame this as explicit versus implicit modeling. So in physics-based numerical weather prediction, everything has to be explicit. If you want an output for a certain thing, you need to model the physics behind it in some way. So they get the input state, do explicit physics calculations, and then run all the Navier-Stokes, and with regional models, they run on the finer grid and so on to capture all those convective processes. And then you get the cyclone trajectories. Whereas with AI weather prediction, there's the training on the historical data, and that training process outputs a bunch of learned weights, or just millions of numbers, that define how the neural network, the deep learning model, processes that data to produce the prediction. And then once you've trained the model, you get your input state, which is actually the same as the input state for a physics-based model, just the atmospheric analysis state. Pass that through the model and you get your cyclone trajectories. The AI model doesn't need to simulate those really fine-scale physics in order to capture, say, intensity changes in tropical cyclones. A really surprising result is that FMV3 only sees that low-res quarter-degree ECMWF analysis state at T0. But I've just shown you that it does really quite well on intensity prediction. So how is that? Well, a kind of hand-wavy answer is that the secrets of cyclone intensity are hidden somewhere in that quarter-degree atmospheric state from the surface to the stratosphere across various geophysical variables. And FMV3 has somehow learned to find these secrets in order to predict rapid intensity changes.